Welcome to the forces tutorial. Forces are the cause of motion, and the simplest way to define the word force is to call it a push or a pull, which may sound silly and very unscientific, but it works, right? A force is a push or a pull on an object. And there's really, we said, 4 fundamental forces that we have to know about, but for this part of the course we're going to just focus on 2, gravity and electromagnetism. And we're going to break electromagnetism into 3 forces: friction, the normal force, and the applied force. They're all electromagnetism, but you call electromagnetism different things in different situations. So we're going to go over when and where you call different forces different things. Let's start with friction. So we have this cute picture of a polar bear sliding around on the ground. Friction is a type of electromagnetism, and you can see I'm abbreviating electromagnetism capital E, capital M, because it's a really long word and I don't want to keep writing it, and you don't have to either. So what is friction? Well, it's a force that opposes motion, and it's caused by attractions between molecules in the 2 objects that are either sliding past each other or sitting on top of each other. And if you don't really understand molecules and atoms yet, that's okay. We're going to talk a lot about that later in the year. But for now, what you want to do is you want to say to yourself, okay, the polar bear is made up of atoms and molecules. And those atoms and molecules actually stick together and form the polar bear. And the ground is also made up of atoms and molecules, which stick together to make the ground, or to make the ice. But those molecules in each of those objects push against each other when they come into contact and push the 2 objects apart, which is why the polar bear doesn't just sink into the ground and become part of the ground, and the ground doesn't just seep up into the polar bear and become part of the polar bear. So each object's atoms are actually pushing apart each other, and when 2 atoms push each other apart, we say that they repel each other. So the verb is to repel, but you can also refer to a force as being repulsive. And it's possible somewhere along the line you've heard the word repulsive used to describe something that's ugly, but what they really mean is that it's so ugly that it repels you, it makes you back up. That's what people mean when they use the word repulsive like that. But atoms can repel each other, but they can also attract each other. It depends on the circumstances and what types of atoms they are. So the polar bear's atoms and molecules are attracted to each other. That's what holds them together in the polar bear. But they repel the atoms of the ice. Here's a microscopic picture of what's happening when 2 surfaces have friction with one another. You can see I'm using the example of the tire of a car running up against the surface of the road. At the microscopic level, if you could get in there with a microscope, you'd see that the tire and the road both have these uneven, rough surfaces. They might look totally flat to you, but actually there's a lot of nooks and crannies, and you can see that on the left-hand side. If you zoom in even closer, you can see that the actual atoms are what make up those nooks and crannies, and you can see the little red line here, right there, showing a force of repulsion between the blue and the green molecules, or that could be a force of attraction. Some molecules are attracted to each other, some repel each other. In the case of friction, it's the attractive forces that cause friction, because as the tire tries to move over the road, some of the molecules in that tire become attracted to some of the molecules in the road, and the nooks and crannies increase the amount of time they're in contact with each other, which means that the more rough a surface is, the more opportunity there is for atoms in one substance to become attracted to atoms in the other. This is why ice is not particularly good at acting like a frictive surface, right? Things slide easily on ice. There's really very little friction on ice. That's because microscopically, when you look at ice, it doesn't have all those nooks and crannies. It's very, very smooth. And as a result, it has a tendency to allow other objects that are on top of it to just slide right past. Because even though there might be some attraction between the polar bear and the ice, there's not a lot of nooks and crannies for that attraction to happen in. And ice is like that really because the little nooks and crannies in the ice actually get filled in by liquid water. So it makes it really hard for ice to be good at stopping you. Another type of the electromagnetic force is called the normal force. And the normal force is caused by the repulsion between molecules, and it's the force that's always perpendicular to the point of contact. And I know that sounds really scientific-y, but here's what I mean. Look at the two people on the slide. The person in the red shirt is sitting on top of the slide. Gravity's pulling him down, and you can see there's an arrow pointing down, representing the force of gravity. At the same time, the slide's molecules are pushing against that guy's butt, right? They're pushing up on him, and that's the normal force. That's the electromagnetic repulsion of the slide's molecules pushing against the molecules in that guy's genes, I guess, right? It's pushing him up. And that's why he's not moving. Even though gravity's pulling him down, the normal force of the slide is pushing him back up. The guy in yellow, who's actually sliding down the slide, he has gravity pulling him down. He still has the normal force, but look at the direction of the normal force. The normal force for him is perpendicular to the slide. The slide is at an angle, so the normal force is at an angle now. So it tilts up at sort of what looks like to you a 45-degree angle, but it's a 90-degree angle with the slide. I'll show you what I mean. Here's his normal force. Whoa, here's his normal force, arrow, right there. And to you, you might be thinking, oh, that's a 45-degree angle with the ground, but it's a 90-degree angle with the slide. See that? It's perpendicular. That's what perpendicular means. It means it makes a 90-degree angle with something. So the guy in the yellow shirt is actually moving because even though the normal force and the force of gravity are sort of equal to each other, they're not in opposite directions. So gravity's able to pull the guy in the yellow shirt down the slide. So both the guy in the yellow shirt and in the red shirt are experiencing the normal force from the slide. The slide is repelling the molecules in their bodies and holding them up. But because the forces are in different directions, the two different sliders have different motion, right? One's just sitting there and the other one is actually being pulled down by gravity. The final type of electromagnetic force that I want to talk about is the applied force. And you might have heard the word apply used as a verb, right? So, apply yourself to your schoolwork, or apply, zit cream to that pimple, stuff like that. To apply means to put to use or to put into action. So an applied force is a force that you put on an object. Usually it's a person, but it can also be another object. So an example of the applied force would be you pushing a block, like you see in this picture. So your push is actually happening because your molecules in your hand repel or push away the molecules in the board. And you're using your muscles to put some oomph behind it, but all of the oomph that you're putting behind it is also coming from the electromagnetic force. But we refer to this as an applied force.